Here we're looking at a pump trainer unit where you have an electric motor going through a magnetic coupling, going to a centrifugal pump with an acrylic housing. It's a great trainer unit. It's useful for illustrating lots of different principles, but I'm going to focus here on the magnetic coupling. This particular coupling right here, as you can see, has a gap between the shaft of the motor over here and the shaft of the pump over here. I'm trying to hold the camera in a way you can see clear through that gap. But just to demonstrate the gap is indeed true, you can see right here I am taking this piece of paper and putting it inside the coupling. So there is no direct solid mechanical connection from motor to pump. This is by magnetism. Now I can turn it like this and it will slip. You can actually see the pump disc right over here will rotate as I rotate the motor side, but it drags behind a little bit. It's not a perfect coupling. It's more like what you might expect with the fluid coupling. It's magnetic in nature. This is using Lenz's law. As magnets are rotated past a conductive metal surface, they induce eddy currents inside the conductive metal. Those eddy currents in turn produce their own magnetic fields that react in such a way that tries to drag it along with the original rotation of the magnets. So kind of like a rotating magnetic field in a three-phase motor, similar thing, except here it's not electromagnets, it's actually real magnets being rotated. So if I'm not mistaken, it looks like the magnets are embedded in this, and this is a copper disc. That copper being the conductive material that the eddy currents are being induced in, the magnets being right here. It could be the other way around, it would still work the same. So we have here a magnetic coupling, and this is advantageous for several reasons. One is alignment. If you have a magnetic coupling, your shafts do not have to be perfectly aligned, which is fantastic. Alignment is a maintenance-intensive task. It's very important to reducing vibration if you have a mechanically coupled pump. But here, if there's no mechanical coupling directly, just magnetism, you can be misaligned and it will still work just fine. Also, let's say if the pump were to become seized for some reason. If the pump were to suddenly become seized or jammed due to debris coming in the impeller or a bearing seize or something of that nature, you will not lock up the pump. You'll not impose such a harsh load on the pump as you would with a direct mechanical coupling. There's some give in this, which will help save your motor. So it's a neat device, and it's something that has wide application in industry. There are pumps with the magnetic couplings built in. You can actually purchase pumps that are pump motor assemblies, and the magnetic coupling is inside its own housing. It's not exposed like this. You can't even see it, but it works the same. It has the same advantages. Also, I've seen systems where a pressure seal is actually done this way, where the gap between the disc and the magnets actually has a non-magnetic material, non-conductive material in between that acts as a pressure seal. So you could actually do your seal this way. So all the pressurized fluid is on one side of the coupling and your atmospheric vented exposure is on the other side of the coupling. Very neat principle, lots of applications.